Imagine a molecular game of musical chairs, but played with high-stakes chemical bonds. This is the SN2 reaction, a single, explosive step where one group kicks another out. Let's meet the key players. First, we have the substrate, featuring a central carbon bonded to a leaving group, which is ready to depart. On the other side, we have our nucleophile, a rich source of electrons looking for a positive target. What makes the SN2 reaction special is that it is concerted. This means the bond making and bond breaking happen at the exact same moment. The nucleophile performs a backside attack, pushing its electrons into the carbon. As the new bond starts to form, the leaving group is pushed out simultaneously, taking its bonding electrons with it. Because this entire swap happens in one single step, both players must collide for the reaction to occur. This is why we call it bimolecular, the 2 and SN2. If you double the concentration of either the nucleophile or the substrate, you double the speed of the entire reaction. Why does the nucleophile always attack from the back? It's not just to avoid crowding, it's a fundamental rule of molecular orbitals. The carbon-leaving group bond has an empty antibonding orbital, the sigma star, with its largest lobe pointing directly opposite the leaving group. To donate its electrons, the nucleophile must target this exact spot. Let's visualize this spatial arrangement. Here is our central carbon, with the leaving group on the right. The three other bonds point away, resembling an open umbrella. The nucleophile must approach from the left, at a perfect 180-degree angle relative to the leaving group. This backside trajectory leads directly to a highly symmetric, high-energy transition state. In this fleeting moment, the central carbon is temporarily bonded to 5 things at once, adopting a flat, trigonal bipyramidal geometry where the 3 non-reacting groups lie in a single plane. As the nucleophile forces its way in and the leaving group is squeezed out, we reach the absolute peak of the energy hill, the transition state. This is not a stable intermediate. It is a fleeting, high-energy arrangement that exists for only a single molecular vibration. If we could freeze time at this peak, we would see a highly symmetric pentacoordinate carbon. The 3 non-reacting groups are pushed into a flat, planar arrangement like the spokes of a wheel, while the nucleophile and leaving group lie along a straight line perpendicular to that plane. Notice the partial bonds, represented by these dashed lines. The incoming nucleophile and departing leaving group share the negative charge, each carrying a partial negative charge. This collinear alignment is key to the stereochemical outcome of the reaction. As the nucleophile completes its bond to the carbon, the leaving group departs entirely, taking its bonding electrons with it. This causes the other 3 groups to flop over to the opposite side, exactly like an umbrella blowing inside out in a strong gale. Let's draw the final chemical product. Notice how the nucleophile is now bound on the left, while the 3 original substituents, which used to point to the left, are now pushed entirely to the right. This complete reversal of spatial arrangement is called inversion of configuration. Because the SN2 mechanism is concerted and forces this backside attack, it is entirely stereospecific. If you start with a single, pure chiral enantiomer, you will obtain a product with 100% inversion of configuration at that carbon stereocenter.